Okay, in this article, we will try to find the expression for the electric field at a point on the axial line due to an electric dipole. So, this is an electric dipole. It is a system comprising of two equal and opposite charges separated by a finite distance. This is the center of the dipole. And I've told you, axial line is the line along the length of the dipole. This is the axial line. So, observation point is anywhere on the axial line. Either it can be on the right hand side or left hand side of the dipole, right? It's your wish. Suppose this is the observation point where the net electric field due to this dipole is to be calculated. Dipole length, it is considered to be 2a. O is the center of the dipole. And suppose the distance of the observation point P from the center of the dipole is r. So it's pretty clear from this charge, suppose it is 1 and it is 2. So, the charge at 1, its distance from the observation point would be r minus a. This distance is r, this distance is a. So, the distance of the observation point from the charge at point A is r minus a. Similarly, the distance of the negative charge placed at point 2 from the observation point would be r plus a. Right? So, r minus a is the distance of the observation point from the positive charge. R plus a is the distance of the observation point from the negative charge. Now let's represent the vector diagram at point P, because our objective is to determine the strength of the electric field at point P. Positive charge. Now due to positive charge at point P, the electric field would be directed in the outward direction. Electric field lines always emanates from the positive charge. It represents the direction of the electric field. So, from positive source charge, the electric field is directed outward. If the source charge is negative, the electric field will be directed towards, right? So, due to this charge, the direction of the electric field at point P would be like this. Suppose E1. E1 is the electric field at point P due to the charge 1. Now, this negative source charge. Due to this source charge, the direction of the electric field will be towards. So, it will be like this. This is E2. Now, you can note one thing. The length of the arrow representing E1 is longer as compared to the length of the arrow representing electric field E2. It is because electric field at a point due to a source charge obey inverse square law. Now look, electric field we have just now discussed. It's given by limit test charge F vector divided by Q naught. This is the formula for the electric field. If you substitute the value of F over here, F is K, Q1, Q2 by R square. One of the charges is test charge. Test charge will get cancelled. So we'll be left with, in magnitude we'll be left with K, that is 1 over 4 pi epsilon. This will be the source charge, either represented by small q or capital Q, and distance. So this is what I am trying to convince you. Electric field due to a point source charge obey inverse square law. So, using this concept over here, the observation point, its distance from the positive charge is lesser as compared to its distance from the negative charge. So, electric field due to the positive charge at point P would be larger in magnitude. So, that is why the length of the arrow representing E1 is taken much longer as compared to E2. Okay, now coming to the basic fact, what's the angle between these two? 180 degree. Whenever the two vectors are opposite directed, that is the angle between them is 180 degree. Then the resultant is given by difference in the magnitude of those two vectors. And the direction would be along the direction of the dominating vector. So here dominating vector is E1, right? So here the resultant would be E axial. It would be from negative charge to positive charge along the direction of E1. And its magnitude would be E1 minus E2, minus because they are opposite directed. So before doing any sort of mathematical calculations, just through the vector diagram, we can safely conclude that the direction of the electric field at a point on the axial line is from negative charge to positive charge. That is along the direction of the dipole moment or along the direction of the dipole length. Because dipole moment, it is also directed from negative charge to positive charge. Dipole length, it is also directed from negative charge to positive charge. So this is a very, very important conclusion. E axial, it is parallel to P vector and in turn it is parallel to 2a vector. So the angle between all these three is 0. That is, they are parallel to each other, right? So that's a very, very important conclusion. So this is regarding the direction of E axial. Now let's try to find out the magnitude of E axial. So for that, let's determine the strength of E1. Once we represent the vector diagram, thereafter we need to consider only the magnitude aspect, right? Now this is the formula. So 1 over 4 pi epsilon Q R square, distance of the observation point from the source charge. Over here source charge is Q. So its distance is R minus A. So it will be R minus A whole square. E2. Again 1 over 4 pi epsilon. Source charge. Over here source charge is again Q. We are considering magnitude because negative charge has already been taken into account while drawing the vector diagram. So it is Q. And what's the distance of this observation point from the negative charge? That is R plus A. So it will be R plus A square. Fine. Now simply substitute these two values E1 and E2 over here. We'll get the expression for the magnitude of E axial. So E axial, it would be equal to E1 minus E2. We can take this as common, Q over 4 pi epsilon. It will be 1 minus R minus A whole square minus 1 divided by R plus A whole square. Keep solving it and we'll arrive at the result. So we can take LCM. So it would be R square minus A square whole square. Over here it would be R plus A whole square minus R minus A whole square. This is in the form of A plus B whole square, E minus B whole square. You can easily expand it, isn't it? So what we'll get is it will be 4AR divided by R square minus A square whole square. Just expand it. We'll be left with this term only. This can be rearranged. It can be rearranged in this particular manner. Q into 2A into R, and it is 4. So twice divided by 4 pi epsilon R square minus A square whole square. Why I am writing in this manner is because I need to represent the expression of the electric field in terms of the dipole moment. Now remember Q into 2A, the product of magnitude of either of the charge and the separation between them, that is known as dipole moment. It is represented by small letter p. So what to do is E axial, it would be equal to twice Q2A can be represented by p. P represents the electric dipole moment. 4 pi epsilon R square minus A square whole square. This is the expression for the electric field at a point on the axial line due to an electric dipole. And direction we have already discussed. Direction of E axial is from negative charge to positive charge. That is along the direction of the dipole moment or along the direction of the dipole length. This is a special case. This is a special case. That is when the dimensions of the dipole is very, very small as compared to the distance of the observation point from the center of the dipole. So, if this is case is valid, then we say that it is the case of a short dipole. It is the case of a short dipole. So, in such a scenario, A is very, very small as compared to R. So, this is the dipole, and the distance of observation point is very, very large as compared to the dimensions and size of the dipole. So, the higher powers of A can be neglected in comparison to R, isn't it? So, using this, R square minus A square. Now, A is very, very small as compared to R. Therefore, higher powers of A would be still smaller. So, higher powers of A can be neglected when compared to higher powers of R. Therefore, for a short dipole, E axial, it will be represented by twice PR divided by 4 pi epsilon R square minus A square. It can be written as R square to the power square. It will be R to the power 4. So it can further be rewritten in this particular manner. Twice P divided by 4 pi epsilon R cube. This is another very, very important expression. But remember, this expression for the electric field will be used only in case of a short dipole when this condition is valid. Direction remains same, that is E axial is always directed from negative charge to positive charge. One point to be noted is that due to a single charge, single isolated charge, the electric field obey inverse square law. Due to a single charge, electric field varies with the distance r in this particular manner. While due to a dipole, the electric field varies with the distance in this particular manner. So for an electric dipole, electric field at a point do not obey inverse square law. It is inversely proportional to the cube of the distance of the observation point from the center of the dipole.